This is a twist no one saw coming. SpaceX has just announced a complete overhaul of the Starship Flight 10 schedule and objectives. So, it's time to say goodbye to Ship 37 and Booster 16. Their fate was sealed in two major explosions in this flight. It's not that something went wrong. This is all part of the plan to push the vehicle closer to perfection than ever before. So, when's the new launch window, and what exactly is the plan for Flight 10? Let's find out, right now on Alpha Tech. If you're a true Starship fan and want to see this 120-meter monster roar into the sky from Starbase, mark your calendar for August 24th in Boca Chica, Texas. Make sure you get there before 6 p.m. SpaceX has set the launch window for 6:30 p.m. This flight promises to be full of surprises, because SpaceX has completely changed the plan. As I mentioned, Ship 37 and Booster 16 are being pushed to their limits, and there's a high chance it could end with a bang. But before we dive into that, let's check out a major move between SpaceX and the FAA. Just yesterday afternoon, the FAA announced that their requested investigation into SpaceX's Starship Flight 9 Anomaly has wrapped up. There were no reports of public injuries or damage to public property. The FAA monitored and approved the investigation led by SpaceX. The final anomaly report pinpointed the root cause of the lost Starship as a fuel system failure. SpaceX also identified corrective actions to prevent this from happening again. They emphasized that SpaceX can now proceed with Starship Flight 10 launch operations under its current license. Right after the FAA announcement, SpaceX released a super detailed report on the results of Starship Flight 9, including the cause of the explosion. But we'll get to that later. What we've all been waiting for is the exact launch schedule, and this time it looks solid, no delays like before, so you can relax. But that's not all. They also dropped a pretty surprising plan for Starship Flight 10's mission. So now, let's dive in and break it down. Alright, we've got the direct report straight from SpaceX's website, and it's split into two parts covering Ship 37 and Booster 16. Let's start with Ship 37. Unlike previous flights, Ship 37 is planned to be pushed to its limits with some bold goals, like slightly exceeding low orbit to deploy 8 dummy Starlinks, which are the exact same size as real Starlinks. By the way, does anyone here use Starlink internet? Just a side question. This is considered a risky move because, so far, no Starship flight has reached the ideal altitude to deploy Starlinks, around 210 kilometers above Earth. Starship Flight 9 got to 189 kilometers, but that still wasn't enough due to pressure issues that caused it to shake, spin, and go out of control. Even though it didn't hit the target altitude, the PS doors opened, but engine problems meant only about a third of them were actually deployed. For Ship 37, SpaceX has made a series of upgrades to optimize the PS doors so they can handle the harsh conditions of space. They're aiming to surpass Ship 35's altitude record, and if all goes smoothly, they could push up to 230 kilometers, a perfect height for Starlink deployment. Do you think Ship 37 can make it? If yes, cheer it on by commenting, "Go Ship 37" below. Here's a fun fact. Once the Starlinks are deployed, they use ion engines, usually running on Krypton, to adjust their orbit, eventually reaching an operational altitude of about 550 kilometers, or roughly 340 miles. Some satellites operate slightly lower or higher, like 540 kilometers or 570 kilometers, depending on their cluster. But Flight 10's mission doesn't stop there. Reigniting a single Raptor vacuum engine while in space is on the agenda. This is a crucial test for performing retro-propulsion burns, basically slowing down and saving fuel when approaching a planetary surface like Mars in the future. The engines don't run all the time. They only fire to adjust speed and orientation, helping the ship avoid hazards like asteroids. Plus, Mars has a thin atmosphere, so you can't rely solely on aerobraking like we do on Earth. As I mentioned in the previous episode, SpaceX has removed hundreds of ceramic heat shield tiles around the body and on all 4 flaps. In some areas, they even stripped a whole row, leaving the stainless steel exposed. This is to stress test the most vulnerable spots during re-entry. That means the stainless steel beneath will face extreme temperatures, up to 1,600 degrees Celsius or higher, while plunging back through Earth's atmosphere. The goal? To see how the ship holds up if a few tiles go missing. And here's the really interesting part. SpaceX has confirmed that multiple metallic tile options, including one with active cooling, will be tested to explore alternative ways to protect Starship during re-entry. Functional catch fittings are installed on the sides to evaluate both thermal and structural performance. One section of the tile line has been smoothed and tapered to address hot spots observed during Flight 6. Starship's re-entry profile is deliberately designed to push the structural limits of the upper stage's rear flaps at the point of maximum dynamic pressure. So, in this flight, we'll get to see whether the flaps can actually maneuver under these extreme conditions, especially in areas where tiles were removed. If things go wrong, the flaps could partially melt, throwing off balance, and boom, Ship 37 could explode in midair if fire reaches the fuel tanks. But the odds are low. SpaceX's real target is to bring Ship 37 safely through re-entry and achieve a controlled splashdown, collecting valuable data on metallic heat shields and how the ship fares when pushed to the limits. That's the plan for Ship 37, but what about Booster 16? Well, its mission plan is even more thrilling. On Flight 9, SpaceX tried and failed to land Booster 14 using a steeper attack angle. A higher angle slows the descent, meaning the booster needs less fuel for the landing burn, a tweak that could significantly improve efficiency for future missions. By testing how the booster handles aerodynamic forces at these steeper angles, engineers hope to fine-tune flight control systems and optimize overall vehicle performance. But reality didn't cooperate. As Booster 14 approached the designated landing zone in the Gulf, it reignited 12 out of 13 central and mid-ring Raptor engines for the landing burn. Communication was lost immediately after ignition, and the booster experienced an unplanned rapid disassembly just 6 minutes after liftoff, cutting short the first flight of a Super Heavy. The data SpaceX needed never made it back. Enter Booster 16. As a completely new booster, SpaceX is clearly taking the opportunity to retry and replicate that critical experiment under extreme aerodynamic conditions, this time with a slowed, high-angle approach. They'll be closely monitoring how the fuel lines handle pressure, how the Raptor 3 engines perform, and how the Block 3 booster design can be improved. However, the website notes, the Super Heavy booster will attempt these experiments while on a trajectory to an offshore landing point in the Gulf of America and will not return to the launch site for catch. And, landing in the ocean with a vehicle not designed for it is extremely risky. If the engines fail to reignite, the booster would fall freely from 70 kilometers at around 1,171 meters per second. Boom, a massive explosion, scattering metal debris everywhere. SpaceX could even face multi-million-dollar lawsuits if it lands in Mexican waters. It's a real possibility, because this is SpaceX we're talking about. After stage separation, the booster will flip along a controlled trajectory before starting the retro propulsion burn. This maneuver was first demonstrated on Flight 9 and requires less fuel reserve, freeing up more propellant for the ascent to orbit, allowing more payload to be delivered. One of the 3 center engines will be deliberately disabled during the final landing burn to collect data on whether a spare engine from the mid-ring can complete the burn. The booster will then rely on just 2 central engines for the final landing burn, hovering like a helicopter above the Gulf, before shutting down and splashing down. If successful, SpaceX will have shown that with only 2 of 33 Raptor 2 engines, it can keep 300 tons of metal hovering in the air, a truly impressive feat. That's all the plans laid out for Starship Flight 10. But are you curious about SpaceX's report on Flight 9? Let me break it down. Booster 14 came in at a much steeper angle than any previous flight, peaking at about 17 degrees. This wasn't by accident. SpaceX wanted to see just how far the booster could be pushed. As it neared the landing zone, it reignited 12 out of 13 engines for the landing burn. Right after ignition, there was a big energy spike near the tail, and then telemetry was lost. The last data came in around 382 seconds into flight, about 1 kilometer above the target area. What likely caused the fire? The booster structure, especially the fuel lines, took more stress than expected from that steep angle. The loads were just too much, letting methane and liquid oxygen mix. And boom, a fire broke out. For the next tests, SpaceX plans to reduce the landing angle, lowering aerodynamic stress and giving the booster a safer shot at touchdown. Now, let's talk about Ship 35. About 3 minutes after stage separation, sensors in the nose cone started picking up steadily rising methane levels. That trend kept going until roughly 5 minutes after ignition, when the main fuel tank pressure suddenly dropped, while the nose cone pressure shot up. Starship's systems kicked in, compensating for the pressure drop and completing the boost to altitude. It reached the expected speed and performed a SECO, second engine cutoff, without missing a beat. But after engine shutdown, the high nose cone pressure combined with venting caused a big altitude error. The error kept growing until the automated fault system shut down the vent. Because of this, Starship skipped its payload deployment target. High nose cone pressure had created too much load for the payload doors to open properly. The ship slowly corrected its altitude using reaction control thrusters until venting resumed as planned. About 40 seconds later, onboard cameras showed liquid methane seeping into the nose cone, and temperatures on several sensors and controllers started to drop. This triggered Starship's automated safing commands, skipping the space burn and dumping all remaining fuel safely into space. The final telemetry came in about 46 minutes after launch, when the ship was around 59 kilometers up over its designated approach area in the Indian Ocean. The most likely root cause of losing the upper stage: a failure in the main fuel tank's pressurization diffuser. Onboard cameras caught a clear fault in the diffuser box inside the nose cone, right atop the forward dome of the main tank. Pre-flight analysis hadn't predicted it, but SpaceX engineers were able to recreate the failure under test conditions back at their McGregor, Texas facility. Finally, they confirmed that to fix the issues with Ship 35 and Booster 14 for upcoming flights, especially Flight 10 and 11, the fuel diffuser has been redesigned. The new design channels pressurized gas into the main fuel tank more efficiently, reducing stress on the diffuser structure. It's gone through a much tougher testing campaign, able to handle flight-level pressures and lasting 10 times longer than originally expected without failing. Flight 9 exposed critical flaws, but gave SpaceX the exact data they needed to push forward. A redesigned diffuser, a refined landing approach, and rigorous hardware testing have set the stage for a smoother Flight 10. Each setback has fueled progress, building unshakable confidence in the Starship program. So, are you excited to see these improvements in action? If you are, make sure to subscribe if you haven't already. And don't miss Starship Flight 10. See you there. Everyone, please listen. The countdown is almost over. Just a few days to go until Starship Flight 10 finally takes off after nearly 3 months of waiting. And right now, there are some positive signs that SpaceX is determined to launch it right on schedule at 6:30 p.m. on August 24th. Just 2 days ago, SpaceX had workers install the FTS on Booster 16, basically a self-destruct button. Haha, just kidding. Sort of. It's actually critical for safety in case Booster 16 goes out of control and can't reignite its engines while approaching Mechazilla. They can activate this system to prevent disaster, and it also ensures they meet all the safety standards before getting the launch license. And that's not all. Just a few hours ago, SpaceX rolled out Booster 16 to the launch pad, right when most of us were fast asleep. Oh man, they did it at night again, which means the photos aren't going to look as stunning as we'd hoped to really admire this beast. What about Ship 37? Usually the upper stage rolls out after the booster, so there's no road closure schedule for it yet, but it's likely they'll do it on the next day, 22nd. Alright, we'll probably talk about Ship 37 later, because Booster 16 is the real star of this episode. Unfortunately, I have to say its fate on this flight is 50-50, that's mean. There's a 50% chance it survives, and a 50% chance it meets the same fiery end as Booster 14. So, why is that? Well, the truth is, SpaceX has planned for Booster 16 to take over the mission that BE4 couldn't complete. Specifically, SpaceX said, following stage separation, the booster will flip in a controlled direction before initiating its boostback burn. This maneuver was demonstrated for the first time on Flight 9 and requires less propellant to be held in reserve, enabling the use of more propellant during ascent to carry additional payload to orbit. In simpler terms, here's what will happen in Starship Flight 10. Once the Super Heavy reaches about 68 to 70 kilometers altitude, it shuts down all engines and goes through hot staging. The booster then tilts and dives toward the Gulf in a horizontal or angled position to use the atmosphere to slow down. The bigger the surface area facing the airflow, the more drag it experiences. When it reaches the right altitude, the booster flips 180 degrees to stand upright, ready for landing. This flip is controlled by reigniting engines, all 13 center Raptors combined with thrust vectoring on the 3 middle engines, while the grid fins rotate to stabilize and guide its orientation. But here's the shocking part for engineers. This flip actually uses 40% less fuel than traditional landing methods. How is that even possible? On a normal vertical landing, the faster the rocket falls, the more it has to fight gravity during descent, burning a huge amount of propellant. Musk's upside-down approach literally flips that concept. By flipping the booster, it uses gravity as an ally, then fires the engines in the opposite direction to slow down most efficiently. Think of it like the difference between slamming the brakes on a moving car versus performing a controlled drift to bleed off speed. Physically it works, but just one miscalculation, and you could have a tens of millions of dollars fireball. The flip can disrupt fuel lines inside the booster, risking engine restart failure, and the rocket would drop freely into the Gulf. That's why I keep saying it's 50-50. However, if everything works smoothly, this fuel-saving trick is a game changer. It could add 20 to 30 extra tons of payload capacity, enough for Starship to carry about 15 additional Starlink version 2 satellites into orbit. And that's not all. That was just after the flip. SpaceX is taking this landing demonstration to the next level. One of the 3 center engines used for the final landing burn will be intentionally disabled. The goal? To gather data on whether a single backup engine from the middle row can handle the landing burn on its own. After that, the booster will continue the final landing burn, using only the 2 remaining center engines, hovering like a helicopter over the Gulf, before shutting down completely and dropping into the water. This is basically pushing the limits to the edge of danger, which also means they know there's a very real chance Booster 16 could explode. But don't worry, there's every reason to believe it will succeed. After all, B14 was a reused rocket, while B16 is brand new. If the data is good, this gamble could pay off many times over. Think long term. SpaceX is trying to save as much fuel as possible. Every successful flip saves propellant, allowing the booster to carry roughly 25 extra tons of payload. With Starship, each kilogram of payload is worth about $100, meaning each flight could generate up to $2.5 million in extra value. Optimizing costs while ensuring safety and maximizing efficiency, that's the SpaceX way. So if you want Booster 16 to make it back safely, drop a 16 in the comments. But before we can even think about that payoff, Booster 16 has to prove it has fully fixed the issues that caused Booster 14's explosion, especially since it's taking over B14's mission. During Starship Flight 9, after completing the boost phase, Super Heavy returned at a significantly higher angle of attack than previous flights, reaching a maximum of about 17 degrees. This flight path was a test to collect data on the rocket's performance limits. As it approached the landing zone, the booster reignited 12 of the 13 engines planned for the landing burn. The one engine that failed was likely affected by the high angle of attack, which caused unstable fuel flow. Immediately after the burn started, a high-energy event was observed near the tail, followed by a loss of telemetry data. The final data was received around 382 seconds into the flight, at about 1 kilometer above the designated clear area. The most probable cause of the landing fire was higher than expected forces on the booster's structure, specifically the fuel lines, due to the increased angle of attack. Post-flight analysis showed that the vehicle loads exceeded the structural tolerance of the lines, causing damage, which allowed methane and liquid oxygen to mix, resulting in an explosion. For all remaining test flights using this Super Heavy variant, the landing angle will be reduced to minimize aerodynamic forces and reduce the risk of structural failure. That means in Starship Flight 10, SpaceX has reinforced the fuel line structure to prevent sloshing, liquid fuel oscillation, which can cause unusual pressures and structural stress. They have also lowered the angle of attack to reduce excessive pressure on the engine systems. And of course, to prepare for a potential explosion, SpaceX has coordinated with an experienced global recovery service to retrieve any debris that might drift into South Texas or Mexico during these flight tests. Why? Because otherwise, hundreds of millions of dollars in lawsuits could arise. For example, Mexico's President Claudia Sheinbaum had threatened to file a lawsuit against SpaceX over what she described as pollution following the Starship explosion at SpaceX's Starbase after Flight 9. In a press conference held in June, President Sheinbaum said her government was reviewing international laws potentially violated due to pollution from the Starship explosion. She added that the government was considering filing necessary lawsuits over the environmental damage. While no official filings have been made, SpaceX is clearly concerned. On July 19, 2025, they used the rescue vessel LB Jill to recover the tail section of B-13 from the Gulf of Mexico near Brownsville, Texas. The section was then transported to Brownsville Port and moved to the Massey site for inspection and damage analysis after prolonged exposure to seawater. The deeper purpose? By actively recovering debris, SpaceX can show cooperation with the Mexican government and compliance with environmental regulations, helping to ease tensions and reduce legal risks. Now, let's move on to Ship 37, which is carrying a mission just as risky as Booster 16's. While this isn't officially announced, it's almost certain that SpaceX will attempt to restart one of the Raptor engines in the vacuum of space after it has been dormant. Sounds simple, right? But this is actually a key step toward making humanity a multiplanetary species. And the truth is, SpaceX has failed at this many times before. The main challenge? In the vacuum of space, there's no external pressure, so the ignition system and fuel delivery have to work entirely independently and perfectly. Add to that the extremely low temperatures, which can freeze liquid methane and oxygen or damage engine components. The system must maintain the right temperature to keep the fuel liquid and ready to burn. Mars missions require multiple precise engine restarts over months of travel. Getting from Earth to Mars is not a straight line. It's a complex orbital dance that demands perfect timing, even a few seconds off, and you could drift forever in space. To this day, no rocket engine has been designed to reliably restart after months in the extreme cold of space. Fuel can freeze, welds can crack, parts can fail. But if Musk cracks this challenge, Mars becomes truly feasible. And the test itself? Surprisingly simple. Ignite the engine, shut it down, leave it in space for an hour, then restart it. If it works, Elon Musk takes one giant step closer to his Mars dream. But to achieve reliable engine restarts in space, Flight 10 must prove that past fuel leaks have been fixed. Starship is the largest launch system ever built, with 6 engines. The huge fuel mass, thousands of tons of liquid methane and oxygen, puts enormous pressure on the complex fuel system, increasing the risk of leaks. Leaks are a universal problem for all spacecraft to some degree. They can originate from engines, fuel tanks, or various pressurization systems, and even tiny leaks can be catastrophic for Starship. Preventing leaks isn't just about mission success, it's about safety and reliability for a vehicle designed for rapid reuse. Protecting the sensitive systems on both Ship 37 and Booster 16 is critical to withstand the extreme pressures of launch, flight, and landing. This is especially important because Starship is slated to land for the Artemis 3 mission planned 2026, and NASA requires the Starship fuel system to be exceptionally reliable, particularly in the vacuum of space. A leak during Flight 10 could delay NASA's approval process. If Ship 37 completes Flight 10 without leaks, SpaceX moves closer to full reusability, a core factor in cutting costs and increasing launch frequency. The challenges are high, but so are the rewards. The countdown is on, and very soon, the world will see whether Flight 10 can pull it off. If you enjoyed this episode, don't forget to like the video and subscribe if you haven't already, so you can stay up to date with SpaceX's latest milestones. Thanks so much for watching, and always remember, what might seem like impossible dreams are exactly what push us beyond the limits and toward the future. When SpaceX rolled out Starship 37 from Mega Bay 2 last week to prepare for a spin prime test at Launch Pad 1, people noticed something odd. Hundreds of ceramic tiles on the body, and all 4 flaps were missing, seemingly at random. The most curious part? Many tiles were missing along the sides of the alt flaps and forward flaps, making a lot of people wonder, what exactly are they trying to achieve, especially with the flight just around the corner and the Starship heat shield still incomplete? But to clear up all the speculation, SpaceX quickly provided an answer in their Starship Flight 10 update on their website. It clearly stated, The flight test includes several experiments focused on enabling Starship's upper stage to return to the launch site. A significant number of tiles have been removed from Starship to stress test vulnerable areas across the vehicle during re-entry. Oh, sounds a bit contradictory, right? On one hand, they have a clear main goal, to conduct experiments ensuring Starship's upper stage can safely return to the launch site. Yes, this is a crucial step toward full reusability, which could drastically slash the cost of satellite launches and space missions. But here's the catch. Removing those heat shield tiles actually makes things way riskier. Returning to the launch site requires precise control during re-entry, where Starship faces extreme conditions. Temperatures reaching between 1,400 and 1,600 degrees Celsius from atmospheric friction at hypersonic speeds of roughly 7 kilometers per second, and a steep re-entry angle. The vehicle will descend at an incline of about 40 to 60 degrees. Those exposed areas, especially on the nose and tail flaps, are taking the full brunt of thermal and mechanical stress, so much so that they could deform, burn up, and even glow like the surface of the sun. And if that happens, the ship will be gone before they can collect any data. That's why thermal protection has always been one of the hardest challenges in spaceflight. NASA spent decades perfecting heat shield tiles that cost $3,000 each. The Soviet Buran program failed trying to develop a similar system, and even SpaceX has lost rockets over a single missing tile. So why would they take such a bold step? Then Musk asked a question that changed everything. What if we don't bring it back? For future cargo missions to build bases on the Moon and Mars, all 18,000 heat shield tiles would have to be sacrificed to save tens of tons of weight, optimizing for 250-ton payloads in a non-reusable mode. But for Starship Flight 10, reusability is still the priority, so removing all the heat shield tiles isn't an option. Instead, they remove just enough to observe what happens on the exposed surfaces of the vehicle. By doing this, SpaceX has three main objectives. First, removing tiles allows them to deliberately create hot spots on the vehicle's surface, especially around areas like the trailing edges of the flaps and regions directly exposed to extreme re-entry temperatures. This helps them measure exactly how plasma and heat distribute, as well as test the stainless steel frame's strength without full protection. Keep in mind, the stainless steel skin is less than 4 millimeters thick, quite thin, so the welds have to be exceptionally precise. Taking off the heat shield tiles is essentially a way to test whether these welds in the thin steel can withstand the brutal temperatures of space. As low as 2.7 Kelvin, around negative 270.45 degrees Celsius, or negative 454.8 degrees Fahrenheit in the shadow of space, and up to 120 degrees Celsius when exposed directly to sunlight, hot enough to boil water. For example, during Flight 6, several hotspots were identified, which led SpaceX to redesign tile edges into smoother shapes to reduce friction. Removing tiles on Flight 10 expands this testing, focusing on areas experiencing maximum dynamic pressure during re-entry to see if the vehicle can maintain structural integrity without melting or losing control. The insights gained from this will help improve the design for Starship Block 3. Second, this approach shows that SpaceX is building a resilient system rather than a perfect one. Replacing thousands of tiles manually after each space shuttle flight was costly and time-consuming. In contrast, SpaceX is producing Starships at scale, aiming for rapid reusability similar to commercial airplanes.
That's our Gigabay. So we're expanding integration to produce 1,000 Starships per year.
Their philosophy isn't about preventing every risk. It's about accepting risks, gathering data, and designing a system that can recover when inevitable failures occur. Intentionally removing tiles is a bold but sensible move to develop a thermal protection system that's not only reusable but also cost and time efficient for maintenance. This is crucial for a vehicle designed to be produced and flown frequently. Third, and this ties closely to the second point, SpaceX is also experimenting with new types of heat shield tiles. As they wrote on their website, multiple metallic tile options, including one with active cooling, will test alternative materials for protecting Starship during re-entry. Not all tiles are being removed at random. In certain areas, they're being swapped for metallic tiles, some even with active cooling, using liquid methane to sweat and absorb heat. Taking out the old ceramic tiles lets SpaceX test the new ones under real flight conditions, see how plasma flows over them, spot hot spots, and refine future designs. Over time, replacing the fragile ceramic tiles, which make up roughly 10 to 15% of the vehicle's mass, or up to 25%, over 18 tons, with the full heat shield, with durable metallic tiles could cut overall weight, make maintenance simpler, and boost reusability. Previous flights from Flight 4 to 9 showed that ceramic tiles were fragile. They could break or let plasma leak through areas like the flaps, causing structural damage. After each flight, they needed complicated maintenance, exactly the opposite of SpaceX's goal for rapid reusability. Metallic tiles, on the other hand, made from stainless steel or nickel-chromium alloys like Inconel, are 3 times stronger, much less likely to crack, and can handle temperatures of 1,500 to 1,650 degrees Celsius without frequent replacement. Several companies are already exploring metallic heat shields. For instance, UK-based Spaceforge developed the Prydwen tile for their fully reusable ForgeStar satellites. Prydwen is made from a high-temperature alloy and has a special origami-style design that unfolds during re-entry. Unlike fragile ceramic tiles that must be replaced after every flight, Prydwen is expected to last between flights, enabling fast, repeated reuse. This shows a clear trend in the aerospace industry toward durable metallic heat shields, and SpaceX is seizing the lead. Overall, the data gathered from Flight 10 is of tremendous strategic importance for the future of the Starship program. This information will directly shape the design of future Starship versions, Block 3, Block 4, all the way to Block 10, potentially sometime in the 2030s. Deliberately creating a high-risk scenario is a big shift for how spacecraft are developed. In traditional programs, a failure during testing is usually a major setback, costly, slow, and frustrating. SpaceX, however, treats each failure as a controlled experiment, turning it into valuable data that speeds up the development cycle. Flight 10 perfectly shows this in action. By intentionally taking risks, SpaceX can gather information that normal flights could never provide. Even if Ship 37 burns up during re-entry, the mission could still be considered a success as long as the data they need is collected. This isn't about perfection, it's about learning fast. If Flight 10 proves the effectiveness of the new TPS technologies, it could be a huge breakthrough. Not only would it help Starship achieve rapid reusability, but it could also reshape the whole philosophy of spacecraft design, making future ships more resilient, simpler, and cheaper to operate. So, do you want Ship 37 to make it back safely, carrying all that precious data? If you do, drop a Go Starship in the comments to show your support. Now, to keep the story going, I'm about to reveal a secret Elon Musk has been keeping about the real goal of Starship Flight 10. It's that they're gradually exploring a single-use Starship configuration, a concept Musk himself has considered. So, what would a single-use Starship look like? When asked about it, Elon explained, "The upper stage might fly or it might not. It's an option. When you want to reuse Starship, re-entry becomes a major challenge. The energy that needs to be dissipated during re-entry doesn't just increase with speed, it increases with the square of speed. That means even a small boost in velocity leads to a much larger rise in temperature. In a single-use Starship, you don't need any of the usual systems. No heat shield, no control flaps, no landing legs, and no extra fuel for a controlled return. That mass, it can go straight to the payload. The whole vehicle is basically optimized to carry cargo into orbit, or even farther. The result is a huge boost in payload. SpaceX says a single-use Starship could carry up to 250 tons to low Earth orbit. To put that in perspective, Skylab weighed about 76 tons. So one Starship could lift more than 3 Skylabs in a single flight. And the entire International Space Station, about 420 tons. That's just 2 flights away with a single-use Starship. It's crazy to think about. With this kind of capability, you could either send massive cargoes to low Earth orbit or launch huge spacecraft deeper into the solar system. Personally, I'm excited about missions carrying enough fuel to perform a burn, flip, burn strategy, reaching destinations much faster without relying on years of gravity assists. Right now, most interplanetary missions require multiple flybys of other planets to gain speed, which extends mission time and increases the risk of failure as systems degrade over time. Take ESA's Jupiter Icy Moons Explorer, launched in 2023 to study Ganymede, Callisto, and Europa. Before it can reach Jupiter, it needs 4 gravity assist flybys, including 3 past Earth, and it won't leave the inner planets until 2029, finally arriving at Jupiter in 2031. Or look at NASA's Europa Clipper, launched last year, which will fly past Mars and Earth before reaching Jupiter in late 2026 and arriving in 2030. These missions are perfect examples of why using a fully expendable heavy-lift vehicle can drastically speed up exploration. And you don't need to go all the way to Jupiter to see a single-use Starship in action. NASA's Starship Human Landing System for the Artemis moon missions is essentially a single-use version. Unlike a standard Starship, the HLS has no atmospheric heat shield or aerodynamic control surfaces because it's not designed to return to Earth. Instead, it's fitted with specialized insulation to protect against micrometeoroids and orbital debris while minimizing heat from the Sun and Earth, critical for preserving liquid oxygen and cryogenic methane during long-term orbital storage. SpaceX's ultimate goal is to turn the HLS into a permanent moon outpost, but since it won't be coming back, it isn't exactly reusable like the full Starship fleet Elon envisions. That raises an important question. If there's a long gap before a return mission reaches the lunar outpost, how will medical issues be handled? In fact, NASA and Google are developing and testing an AI-based medical assistant to support astronauts. In June, Blue Origin's CEO, Dave Limp, announced that the second launch of the New Glenn rocket was scheduled for August 15th. He also shared that the team had completed a successful hot fire test of the rocket's second stage engine back in April, a big milestone for the program. This next mission, titled Never Tell Me the Odds, carries a major objective: landing and recovering the booster, something the company wasn't able to pull off during its first attempt earlier this year. But while excitement is building, there's also plenty of doubt about whether that August date is realistic. A mid-August launch feels like a tight squeeze for Blue Origin, especially in light of some troubling internal reports. According to Ars Technica, the date may have been set more to satisfy Jeff Bezos than because the rocket will be ready. Progress has been slower than hoped, and the company is already on track to miss its ambitious target of 8 launches in 2024. Adding to the uncertainty, Ars Technica also revealed the sudden departure of Jarrett Jones, the senior vice president overseeing the New Glenn program. His exit came just after news broke about the rocket's sluggish pace, sparking speculation that it might be tied to Bezos' dissatisfaction with the project. As time passes, those earlier predictions are proving true. By mid-August, instead of watching another New Glenn take flight as planned, we got a different update from Blue Origin. New Glenn's second mission is net September 29th. We have been working closely with NASA on the timeline and look forward to flying Escapade to Mars. You'll start seeing some exciting things happening at the pad down in Florida very soon. That tells us 2 important things. Never tell me. The odds has been pushed to late September, just as many expected, and the payload is now officially confirmed, a pair of small spacecraft headed to Mars to study the planet's magnetosphere. So, what about this new launch date? With over a month left on the clock, the big question is, can Blue Origin actually hit that late September target? Or will it slip again into October? From the limited updates we've seen from Blue Origin and Dave Limp, we know they've successfully completed the aft module activation test. This involved firing up the hydrogen peroxide system that powers the aft module's hydraulics and running a simulated short mission, essentially proving the rocket can handle complex operational demands. This comes after the forward module testing in July, which also focused on activating a hydrogen peroxide system, this one powering the reaction control system. The next major step is to attach the aft module to the rest of the first stage, GS1, and install all 7 BE4 engines. That's a massive milestone in itself. Each BE4 generates about 550,000 pounds of thrust at sea level, and getting all 7 installed is no trivial task. After that comes the static fire test, followed by vehicle assembly and rollout. This final stage means stacking GS1 with the second stage GS2 inside the integration facility, then moving the fully assembled rocket to Launch Complex 36 for liftoff prep. Next on the checklist are integrated tests at the launch pad, including a wet dress rehearsal, full fueling of the rocket without ignition, where the entire vehicle is operated as one cohesive system. Once that's complete, Blue Origin and NASA will attach the payload, then move on to final checks. In the meantime, Blue says it's working closely with NASA and teases exciting things happening at the pad very soon, which will also involve monitoring weather conditions as launch day approaches. If all goes well, the last obstacle before liftoff will be securing the FAA launch license. With just 45 days remaining until the September 29th target, Blue Origin still has a heavy workload ahead, meaning they'll need to pick up the pace if they want to stay on schedule. The company follows a gradatim ferociter philosophy, Latin for step-by-step, ferociously, favoring methodical, safety-first testing over rapid iteration. This stands in sharp contrast to SpaceX's fail-fast, learn-fast approach. For perspective, New Glenn's development began in 2015, but its first flight didn't happen until January 2025, following a successful hot fire in December 2024, a full decade in the making. That's more than twice as long as SpaceX's Falcon 9, which went from concept to first launch in about 4.5 years, and matches the timeline of ULA's Vulcan rocket, which also uses BE4 engines but has already flown 3 times. Blue's slower pace reflects a mix of supply chain hurdles, like delays in BE4 production, extensive ground testing, and its early focus on making New Glenn reusable from the start. But is New Glenn moving unjustifiably slowly? Not really. Building rockets is hard. Designing for reusability adds even more complexity, with features like landing legs and grid fins, and Blue Origin is making the leap from suborbital to orbital flights, while also qualifying its BE4 engines, which faced combustion instability issues during testing. Compared to Boeing's Starliner, which has seen decades of delays, or ULA's Vulcan, which finally launched in 2024 after years in development, Blue's pace is actually moderate. In some ways, Blue Origin can take pride in the fact that it could potentially reach the Moon and Mars before SpaceX or even China. There's logic behind that. These specific missions are less complex and relatively modest in cost, making NASA more willing to accept the risk. Take NASA's Escapade mission, for example. With a budget of about $79 million, it's significantly cheaper than any Mars mission NASA has sent in recent years. The mission involves 2 spacecraft designed to measure plasma and magnetic fields around Mars. By gathering data from 2 positions simultaneously, scientists hope to better understand the processes that strip atoms from the planet's magnetosphere and upper atmosphere, processes that influence long-term climate change on Mars. Escapade belongs to a newer category of small planetary science missions, where scientists can propose relatively low-cost probes to explore the solar system. The lower price tag means NASA can accept more risk, something they wouldn't do with a billion-dollar Mars mission on an untested rocket. Originally, Escapade was slated to fly on New Glenn's debut mission in October 2024, but due to uncertainty around the rocket's first launch date, it was pulled from that flight. The challenge was that once the 2 spacecraft were fueled with hypergolic propellants, they had to launch within a limited time window. Had Escapade launched last October, the probes would now be approaching Mars and starting their science operations. Missing that 2024 Mars window means they've had to wait for the next one, which opens later this year. As a result, the current plan is to launch this fall, but the spacecraft won't reach Mars until late 2027. Blue Origin is also targeting a moon landing in summer 2025 with its Pathfinder mission, designated MK1-SN001. This will be a key demonstration of the capabilities of the company's first Blue Moon lunar lander, Mark 1. The Pathfinder mission will test the BE4 engine, cryogenic fluid power and propulsion systems, avionics, reliable communications, and, most importantly, its ability to land within about 328 feet, 100 meters, of a target. It will also carry NASA's science payload to the Moon's south polar region. A major objective is to study how the lander's engine plume interacts with the lunar surface using NASA's SCALP-SS stereo cameras for lunar plume surface studies to prepare for future crewed landings. Compared to SpaceX's first uncrewed Starship lunar landing, scheduled for 2026, Blue Origin's Pathfinder mission is far simpler. The Mark I is just 8 meters tall, half the height of the future Blue Moon. Mark II and much smaller than SpaceX's Starship HLS. It's designed for modest missions, carrying about 3 metric tons of cargo, but makes up for its smaller scale with a simpler design. This expendable lander uses a single launch approach. New Glenn will place it directly into a lunar transfer orbit, with all the fuel for the journey and landing already on board. No multiple launches, no in-space assembly. Just a straightforward plug-and-play mission that reduces risk and complexity. That could give Blue Origin an edge in reaching the moon before its competitors. Starship HLS, by contrast, is a massive, multi-stage spacecraft that requires in-orbit refueling to get to the moon. Even for its uncrewed demo, SpaceX plans to launch the full crewed Starship HLS design without astronauts aboard. Multiple successful Starship launches would be needed just to refuel the lunar vehicle in space, adding layers of complexity, deep space operations, precision landing the largest rocket ever built, and developing technology never flown before. Testing has also been a hurdle for Starship, with ongoing flight trials in Boca Chica facing setbacks that have delayed progress. While Blue Origin is building a small, robotic cargo vehicle, SpaceX must prove a far more complex system before it can even attempt an uncrewed landing. NASA's requirements add more pressure. Before astronauts can fly, SpaceX must first complete a fully integrated mission, including an uncrewed moon landing and in-orbit refueling. These milestones are challenging, and recent test issues make it more likely Starship's uncrewed landing will slip into 2026. By comparison, the Blue Moon Pathfinder is lightweight, uncrewed, and not designed for crew transport, meaning far fewer regulatory and technical hurdles. No docking, no fuel transfers in space, just a streamlined mission profile that allows Blue Origin to move faster with fewer risks. It's not just the straightforward design of Blue Origin's lander that could give the company an advantage. They've also been gaining valuable lunar experience through partnerships, even without having landed one of their own spacecraft on the moon, yet. One example is PlanetVac, an innovative low-cost sampling system aimed at enhancing the scientific returns of missions to worlds like the moon. It works by releasing a burst of gas onto the surface, which kicks up lunar soil, regolith, into a container for onboard analysis or potential return to Earth. PlanetVac's strength lies in its simplicity, with only one moving part, a valve to release the gas. Compact enough to mount directly onto a lander, it was created by Honeybee Robotics, which is now part of Blue Origin. Another is Lister, short for Lunar Instrumentation for subsurface thermal exploration with Rapidity, a sophisticated drill capable of digging 3 meters into the moon's dusty terrain. Every 50 centimeters, it pauses to place a thermal probe that measures heat flow, tracking how temperature changes with depth and how well the material conducts heat. This information helps scientists better understand how the moon's interior has evolved, according to project lead Dr. Seiichi Nakahara. SpaceX and Blue Origin have long been rivals, like fire and water. Their tense relationship first sparked years ago at a gala dinner following a tech and rocket conference, where Jeff Bezos and Elon Musk had a heated debate over ideas for space technology. That disagreement marked the beginning of what would become one of the most intense rivalries in the aerospace industry. Things really escalated in 2013, when the two companies went head-to-head over leasing Launch Complex 39A at Kennedy Space Center. SpaceX ultimately won the contract, prompting Blue Origin to file a legal challenge and lose. Then, in 2014, tensions rose again when SpaceX sued Blue Origin to invalidate a patent related to landing rockets at sea. Once again, SpaceX came out on top. But perhaps the most public showdown happened in 2021, when Blue Origin sued NASA for awarding the Artemis lunar lander contract to SpaceX. That case was thrown out as well. Fast forward to June 2024, and Blue Origin has once again taken aim at SpaceX, this time asking the FAA to limit the number of Starship launches from Kennedy. The move sparked fresh controversy, with Elon Musk slamming it as nothing more than a lawfare to slow down the competition. After repeatedly losing on the battlefield, Jeff Bezos still hasn't let go of his fierce rivalry with Elon Musk. Behind the scenes, Blue Origin has been quietly making moves, developing in the shadows, biding its time, and waiting for the perfect moment to strike back and catch SpaceX off guard. And that became even clearer on July 12th when Blue Origin began reposting updates from their CEO, Dave Limp, showcasing real progress on their BE4 engine production. In one post, Dave shared a glimpse inside their Rocket Park engine shop, now starting to feel a little crowded in the best way possible. Rows of completed BE4 engines are neatly lined up, and according to Dave, the full set of 7 engines for New Glenn's second flight is ready, along with a spare. The photo shows at least 8 engines on standby, awaiting their turn to head to the launch pad. But that's not all. Dave also revealed that several BE3U engines, designed for future New Glenn missions, were hot-fired back in April and are fully prepped for action. Perhaps hidden beneath the surface of these 2 posts is a deeper message, a quiet desire from Blue Origin to be recognized by SpaceX, a signal that they're no longer lagging behind, but becoming a real threat. Their engine production pace has clearly reached a new level, and these very engines could be the key to helping New Glenn outshine Starship for the second time. So, why the second time? Well, on January 16th, during New Glenn's first flight, which just so happened to fall on the same day as Starship Flight 7, Blue Origin pulled ahead. Their rocket successfully reached orbit, powered by engines that burn the same combination of propellants that SpaceX uses: liquid methane and liquid oxygen. And that's not all. These very BE4 engines are also what Blue Origin is counting on to carry New Glenn to the moon, possibly as soon as March 2030. Because while SpaceX's Starship HLS may have been selected for Artemis 3, Blue Origin isn't out of the game. In fact, NASA awarded them a $3.4 billion contract to develop their own lunar lander using New Glenn as the launch vehicle to make that moon landing happen. That's exactly why SpaceX should start seeing Blue Origin as a serious threat. Because just one major success from Blue Origin, one moment in the spotlight, could be enough to overshadow SpaceX and shift all the criticism their way. But even so, there are several reasons why Elon Musk still doesn't feel threatened. Let's talk about Blue Origin's engine production pace first, something they've been pushing harder than ever before. The company is now fully committed to building more flight-ready BE4 engines than at any point in its history. Blue Origin's engine manufacturing efforts are centered around 2 strategic locations: Washington and Alabama. But it's their presence in Huntsville, Alabama, that has quietly become a rising star. Nestled within Cummings Research Park, Blue Origin's rocket engine factory there has been expanding rapidly, growing to 400,000 square feet in 2020 and adding another 200,000 square feet in 2024, a phase that has already been completed. Looking ahead, the company plans to scale up even further. Shane Davis, Huntsville's Director of Urban and Economic Development, revealed that future expansions are already in the pipeline. With this kind of manufacturing footprint, a significant number of BE4 and BE3U engines are expected to be produced here, putting Blue Origin in a much stronger position to compete with SpaceX's Raptor engines. And they've already started ramping up. Since October 2023, production has been accelerating. In the 3 years since the Huntsville facility opened, it reportedly exceeded its original production targets. While Blue Origin hasn't released official numbers, multiple sources suggest they are now building dozens of BE4 engines per year. These engines power both New Glenn, which requires 7 BE4 engines for its first stage, and a BE3U for its second, and ULA's Vulcan Centaur, which uses 2 B4 engines on its booster stage. Elon Musk is probably well aware of all this. And honestly, you can almost imagine him laughing and saying, "Is that all?" Because compared to SpaceX, Blue Origin still has a long way to go. Right now, SpaceX produces its Raptor engines primarily at its McGregor facility in Texas, with additional support from a plant in Hawthorne, California. The focus there is on mass-producing Raptor 2s and developing the next-generation Raptor 3, which is expected to enter large-scale production by the end of this year. As for Raptor 2, SpaceX announced it had reached a production rate of 1 engine per day by the end of 2022, roughly 365 engines per year, assuming a steady pace. A report indicated that around 200 Raptor 2 engines were built in the first 11 to 12 months, putting the average somewhere between 16 to 18 engines per month. That said, SpaceX has recently slowed production a bit to focus on improving quality, so the actual output may now be closer to 300 engines per year, depending on launch cadence and hardware needs. Then there's Raptor 3, the engine that's about to exit the development and testing phase. With Starship Block 3 expected to debut later this year, Raptor 3 is on its way. There's no official word yet on full-scale production numbers, as it's still in limited test builds. According to Elon Musk, the goal is to significantly boost performance while cutting costs compared to Raptor 2. So far, it's estimated that around 50 prototype units have been built, though SpaceX hasn't publicly confirmed that number. Looking ahead, production volume for Raptor 3 is expected to ramp up as the design is finalized, potentially matching or even exceeding the output of Raptor 2, somewhere in the range of 300 to 400 engines per year. But that's just the beginning. SpaceX is aiming for far more. According to Musk, the long-term goal is to produce 1,000 Starships per year. That would require 30 to 40 Raptor engines every single day. As Musk put it during his Mars presentation just over a month ago,
Ultimately, we're aiming for the ability to produce 1,000 ships a year, so 3 ships a day.
but beyond just production speed, it's the engine itself that really matters. The technology, the performance, and the long-term vision behind it. Jarrett Jones, Senior Vice President of the New Glenn program, acknowledged this during his speech at Satellite Business Week on September 11, 2023. He openly admitted, "Of course I watch SpaceX's success, because that's our future." And he's not alone. Much of what Blue Origin is doing today builds on the foundation SpaceX has already laid. A perfect example? The BE4 engine. It's a massive power plant, producing 550,000 pounds of thrust, and it's designed with high throttle ability in mind, a must-have for landing reusable boosters softly and safely. Unlike traditional kerosene-based engines, BE4 runs on liquefied natural gas. Why? Partly because it burns cleaner at low throttle settings, but also because LNG's cryogenic properties make it easier to pressurize propellant tanks without relying on external helium systems. It's a practical solution, and one that echoes SpaceX's own choices with methane-powered Raptor engines. Inspired by Raptor, BE4 uses an oxygen-rich staged combustion cycle, a more complex but far more efficient design. In this setup, a small portion of the fuel and oxidizer is diverted into a pre-burner where it's combusted to generate hot gases. These gases drive the engine's turbines before flowing into the main combustion chamber. The result? A closed-loop system that wastes nothing. This approach is far more efficient than older engine designs that simply dump exhaust or rely on separate power sources to spin the pumps. Of course, like all rocket engines, it's a balancing act, a series of design trade-offs. Choosing an oxidizer-rich or fuel-rich mixture instead of a perfect stoichiometric burn allows engineers to control internal temperatures and use regenerative cooling to keep the engine's chamber and nozzle from overheating. It all sounds impressive, and to be fair, it is. But even with all that, it still doesn't hold a candle to SpaceX's Raptor 3. Unlike BE4's oxygen-rich stage combustion, Raptor 3 uses a far more advanced full-flow stage combustion cycle, which pushes performance to the next level. It features 2 pre-burners, one fuel-rich and one oxygen-rich, allowing for more efficient combustion, reduced pressure across engine components, and improved durability and reusability. Thanks to this design, Raptor 3 delivers a staggering 280 tons of thrust, with a vacuum ISP of 380 seconds and 350 seconds at sea level. BE4, it maxes out at 245 tons of thrust, and an ISP of around 310 seconds. That's a 21% advantage in raw thrust alone, a difference that translates directly into payload capacity, especially on deep space missions to the Moon or Mars. In short, Raptor 3 doesn't just outperform BE4, it leaves it in the dust. When it comes to the rocket engine race, Raptor 3 holds a massive edge over BE4, not just in power, but in cost and scalability. Each Raptor 3 is estimated to cost around $500,000, thanks to aggressive in-house manufacturing, 3D metal printing, and a focus on mass production. SpaceX had already built over 100 Raptor 1 by 2018, and that pace has only increased since. This level of efficiency is one of the key reasons Starship launches are projected to cost as little as $2 to $3 million per flight. BE4, on the other hand, comes in at a much higher price, around $8 million per engine. Built in smaller batches and used on rockets like New Glenn and Vulcan Centaur, the BE4 simply can't compete with Raptor 3's cost efficiency and production scale. Reliable? Yes. But scalable and economically optimized? That's where Blue Origin still lags behind. So, do you still think Blue Origin stands a chance against a powerhouse like SpaceX?